record. Just sort of your weekly obligatory warning that if you appear in the video, you'll appear in the video, and if you're audible in the video, you'll be audible. Okay, no math today. I know I sort of like gave you guys a ton of math last week, probably scared half class away, but there'll be a payoff, I promise. Other reminders, the pracs and toots start this week. Probably already some of you had a prac or a toot, so you may have had your hands dirty with Haskell. What I'm going to do today, this is going to seem a little bit out of place because there are some ways of doing this course where I develop everything from first principles, and that would be fun, but you wouldn't be able to do anything in pracs and toots or like your assignments for that matter. So I'm just going to give you a little bit of a crash course in Haskell, show you that it can do arithmetic, show you some string operations, just so there's some stuff that you can do in practical. There's also going to be your first assignment, which is going to be deployed this Friday. And I just encourage you to start earlier, especially with some of the Haskell coding, because from my experience, the questions we're going to ask are going to seem really simple. Like you're going to think, I can do this in 10 seconds in Python. It's like, yep, but we're programming in Haskell. And you probably won't be able to do it in 10 seconds in Haskell. So despite the fact they look a little bit easy, and ultimately the solutions will be easy, you should just allocate some time for like struggling with a new programming paradigm, because you leave it till the very end, you may not get done and then try to resort to cheating and I'll have to write you up, which is a huge waste of a lot of people's time. So please don't do it. Okay, so we're just going to work in Haskell today. So the first thing I'm going to do is just show you how to execute the REPL. So you should download Haskell to your machine. It's a pretty big system. So you'll probably delete it at the end of course, but for now you may have to like allocate, I don't know, a few gigabytes to install it. So I'll mostly be working in the read eval print loop. And the REPL or read eval print loop is called the GHCI, right? So the Glasgow Haskell Compiler Interactive. What happened? Okay, if that happens again, all of these dongles in all lecture halls seem to be failing because they bought like probably the cheapest one. But I have a backup. I have to ask if chat, can you still see? Okay. Okay, so this is the normal way I'm going to be demonstrating Haskell code in this class, right? So down here, I have the Unix bash, right? So I can like display files, change directories, so on and so forth. And up here, I have a file. The Haskell file extension is .hs. So you can see on my desktop, there should be this file foo somewhere here. And I should be able to type GHCI, make that a little bit bigger. And that gets me into the Haskell REPL. So you can see, and we'll talk about this at length, I can do arithmetic and stuff like that. But mainly what I'm going to want to do is load sort of this file and then be able to use the definitions inside them. So this will mostly be the way that we'll be learning Haskell, right? By writing. Oh, that sucks. But I bought one, so I won't use the unis ones anymore. Sorry about this, chat. Hopefully that will work. You can still see chat. Sorry, we're having some projection problems here. I think I may have to reshare everything. Okay, so as I said last week, Haskell is a lambda calculus. So everything we're going to be typing into it will be lambda calculus expressions. But we may want to type things into it that aren't lambda calculus expressions, like, you know, quit. Give me info on something, give me the type of something, load something, reload something. So to indicate to Haskell that the string that we're typing is not a lambda calculus expression, you start it with a colon, right? Which indicates, you know, you're actually taking some type of command. So each command has a short form, which I'll use instead. So quit, you can just say Q, info, you can just do I, type, you can just do T, load, you can just do L, and reload, you can just do R. Move this. Okay, so what I'm going to do in my slides is like simulate a Haskell session or my bash. So whenever you see this chevron here, you can just assume I'm working in the terminal. What I'm going to do is launch GHCI. That will come up and you'll see that the prelude has been launch. So the prelude is the standard set of all functions that are available to us. So for instance, we have loaded into Haskell the basic rules of arithmetic. We're not going to have to build them, although we could if we really wanted to. So again, the prelude is a library of standard functions that are loaded by default into the GHCI. If you ever load a new library in, so I'll show you what we do here. So when you're reading code from Haskell files, we're going to be reading in functions and variables. It's a good standard practice to name your file as a module with the same name that you gave it as the file, right? So this is sandbox.hs. So the first line of my file, we're just going to say this is a module called sandbox with a capital S. Haskell is a case sensitive language, where, and then you just put everything that you want into this file. Right? So in this case, I set x is equal to 2. We have comments, of course. So 2 dashes indicates the start of a comment. If you want to do multi-line comments, then you just have to sort of use 2 dashes and curly braces. Everything inside the curly braces is going to be a comment. So again, it's just good practice to name your files as modules, because once we load them, then you'll see that it's the interactive REPL is going to actually give you some indication that that has been loaded. Right, so now we have use of X. Okay, note we can switch prelude out with any prompt that we want. And it's very typical among Haskell programmers to swap this out with this lambda symbol somehow. You may see this online. I certainly am going to swap it out in my slides, if only to save horizontal space, but also just feels cooler, right, to have that lambda in there. So if you want to set your prelude to something else, the other thing is if you load a bunch of libraries, this has the tendency of getting quite long. So you can set your prompt to lambda chevron. It can take Unicode, so you just have to copy paste from this. If you want to make this permanent, you need to find a .ghci file. It's a hidden file in your home directory. You can just put this command into it. When Haskell launches, it's going to launch all of the commands in here first. You just have to make sure that it has the right permissions. So those are the permissions that you're going to need on that file if you want to make a permanent change to your prompt. Now I want to talk about infix versus prefix notation, because we can use both in Haskell, but we have to be really careful because it's sort of not natural to use sort of infix notation in the system, and it's going to be the source of a lot of bugs. So over the course of the semester, I'm going to try to convince you to move from infix notation to the prefix notation because it's much more natural in the Haskell system. So let's just spin up sort of a, someone smell burning? That's something we should be concerned about. Or I hope that's not the projector. Oh boy, if it's not one thing, or it would be the first class something got set on fire that I ever taught. So, okay, well, we'll forge ahead. Jesus, Murphy, if the projector light's on fire, we'll figure something out. Okay, so suppose we have a function, and this function takes something from A, and then something from B, and something from C. Last week, we learned that this is a function which takes a value to a function which takes a value to sort of a constant. We call this O plus, right? So any bivariate function, any function that takes 2 inputs can be, we can utilize the infix notation. And most of the arithmetic that we use takes 2 inputs and returns something. So we mostly use infix notation. So when you have a function which takes 2 inputs, we can call it like this. We can sort of say x, O plus y, right? X plus y, x times y, right? The operation is in the middle. It's inside the expression, thus infix. There's another version of this called prefix, right? Which is actually the more standard way that functions are called. Like you don't normally put the function name in between stuff for invocation. You normally have the function at the front, and then you pass it inputs like this. So when we put the function at the front, which we'll mostly be doing, this is called a prefix notation, right? So you can see in Haskell, that's the infix notation. That's the prefix notation, right? And so somehow this is where we're going to talk a lot about this in the ways that it can be partially evaluated. But this is sort of why we're talking about application so much from last week. In Haskell, we have multiplication, subtraction, addition, exponentiation. this $sign, which we're going to call apply, logical and logical or. And each of these are infix operators. That is, they each expect to take two inputs, and because they take two inputs, can be called in a special way. So subtraction is a pain in my ass. It will probably be a pain in your ass too. I don't actually recommend using it. The fact that we have a symbol which is like does different things in different contexts can sometimes get confusing. There's a function called negate. And it's better to use the unary function negate for a variety of reasons. It's less error prone. And furthermore, it's going to work on anything that is like negatable rather than just the subtraction negation, which will only work on things like numbers. Okay, so extra consideration for subtraction is required. I'm going to show you all the ways that it can go a little bit hairy. Okay, so here's 2 plus 3. Right? This is infix. Now, in terms of our like functional programming model, like we can just presume at this point that somehow we've like put arithmetic into the system somehow and made the plus and numbers available to us. But strictly speaking, this is something that we'd have to build. But last week I showed you that we actually have all of the fundamental pieces of logic. And for those of you who've taken any set theory, all you really need is a set and logic to build numbers. Right? So I could actually show you how integers are built. Maybe we'll do a little bit of tutorial. But at this point, let's just presume that okay, the functional machine we've been given, it's been programmed, it has an abstraction already available to us to allow us to work with numbers. Otherwise, we're not going to be able to do much. Okay, so here's 2 plus 3. No surprise, that gives us 5. This is the prefix notation. So any infix operator, if you put brackets around it, will turn it into a prefix operator. So now we can say plus 2 and 3. And remember, we're going from the inside out. In this case, it didn't matter that much because addition is commutative. That is 2 plus 3 is equal to 3 plus 2. But what happened here is like we're applying from the inside. We're applying this function plus to the number 2, and getting another function back, and then taking 3 and passing it to that function. And we're going to flesh that out more as we go. But in any case, this will give you 5. So infix operators can be made prefix with rounded braces. Okay, subtraction. Here's like some weird scenarios. And one of the issues with Haskell is that you're probably never going to get any type of useful error message. Right? The errors make sense only once like you become like a true expert at Haskell. Like there's errors that I often have to think really hard about. So often we won't even really engage with the errors, right? Because I'd have to explain so much stuff to explain why the error is being given, and it's often not that helpful. At your stage, the best debugging strategy is just to add brackets everywhere. Like normally what happens is that the error is caused by some type of evaluation order problem, and putting brackets sort of solves that. Okay, so 2 minus 3. This better work, right? This is subtraction. What do we expect? Minus 1. What about 2 minus 3, right? This would be totally okay in Python, right? Because in Python, like the syntax here says, yes, like this negate, like from context, this minus should be a negation. And I should be able to add 2 and minus 3. Any guesses? Is that a solid maybe? Right. If you really want to commit to that maybe. Yeah, it's an error. And in this case, it's a parsing error, right? Because Haskell's not really built to like work with infix operations, right? So this isn't the best sort of way of representing this. And you're getting a weird error here, right? It cannot mix plus and the prefix minus, right, in the same infix expression. Well, at least this one's telling you it's a parsing error, right? From this, we can say, okay, I typed something wrong. Okay, what about this, right? I have the plus function and I want to pass it 2 and minus 3. It's error? Okay, yeah, error. Right, this won't work either. We're getting even more of an impenetrable error. No instance for show integer arising from the use of print. What does this mean? Well, I can tell you what it means. So this is sort of not what it seems. This is like the plus operator applied to 2, applied to like the partial application of subtraction. So this actually evaluated to a function. And Haskell's saying like, I can't print functions. Those are just like expressions. So the strategy here would be to bracket stuff, and you'll see that it will work. So anyway, the point of that last slide is be careful when using the negation symbol. And don't be too concerned if you can't understand the errors. Yes, sir.
Still valid Haskell code, just not.
Yep, it's valid. Otherwise, we would have got a parsing error. But it says, yeah, like I have no way of displaying functions, essentially, is what it's saying. Although I was having trouble trying to evaluate it with something. It's not as easy as just giving it another integer. But again, the point is just be really careful with when using the negation symbol. I wouldn't even use it, period, right? If we can at all avoid it. So magic brackets, that solves things, right? That sort of tells Haskell, I want this expression evaluated first. And from the context here, it should be the case that like the minus symbol is negation. I could also say +2 negate 3. That's going to work. And it's going to be more generic. And like genericity is going to be something that we're really going to strive for in this class. You'll see we're not necessarily writing functions over lists of integers. We want to write functions over lists of anything, right? That will work. And we'll see what that means too. We can use the apply symbol here. So because anyone used Lisp here? Like Lisp was a language that used brackets to indicate everything, more or less. And it became so polluted with brackets that people sort of just abandoned it. So Haskell had the same downfall, right? I'm saying use brackets to debug. Okay, but now a lot of our statements are like polluted with brackets. So that's why we introduced this apply symbol. It's kind of controversial. I'll talk about why later. But in essence, it allows us to like dump brackets, right? So instead of bracketing this, I can say, here's the plus function. Let's give it 2, and then everything to the right of that application symbol. So that's also going to work. So like I know at this point, this looks the most sensible. But by the end of the course in this language, I'm hoping that like you'll think this is the most sensible. Because from our lambda calculus model, this is the most close to a lambda calculus expression. Order of operations. So what does this evaluate to? But really, I'm just interested to know what arithmetic you think like happens first. If this system was sensible, yeah. First, I would say exponentiation usually has the highest priority of evaluation. And I would for sure say that multiplication usually has higher priority than addition. But the point is, infix operations introduce ambiguity to the system where we have to like now designate orders of operations, right? If we were just doing this in the prefix manner, we wouldn't need it. There'd be no ambiguity. So this turns out to be 38, so which is 2 + 9 × 4. So if I were to bracket it to describe the order of expressions, it would happen like this. Now, I'm sure all of you are aware of order of operations, but in Haskell, we can ask for for information on any operation or function. And when you ask for it, it's going to give you some information like this. And you're going to become experts at reading information like this, but I'll just walk through it now. So this are type classes, right? So they're sort of like groups of types that act in the same way. So this function in its prefix notation takes something that acts like a number and something that acts like an integer and gives this function, right? So A to B to A. So it's a function that takes 2 inputs and returns an input. And it says it's also can be called infix. It's right associative. It has priority 8. Higher priority means it gets evaluated sooner. And then there's the operation. So let's study this a bit, right? So this is an exponentiation operator that's going to work on like anything that satisfies this type signature. Right? It doesn't care if you give it like 2 integers. It doesn't care if you give it a float in an integer. It does, as long as the thing that you're giving it behaves like a number and the exponent behaves like an integer, you're fine. Right? So given this, do you think we could do 2.1 cubed? Do you think we can do 3 to the power of 2.1? No, right? Because 3 doesn't behave like an integer. And we're going to talk about this later once we do type classes. For now, you can just go ahead and ignore the first part and focus on the second part, right? So the second part basically is like the type header. Right? It takes something of type A, something of type B, and returns something of type A. If we want info on multiplication, we're going to get sort of the same thing. Multiplication takes something from A and something from A and gives you back something from A. And look, this first part doesn't exist. Why? Well, because turns out multiplication is a operator that can be applied to like a ton of stuff. We don't necessarily just have to have multiplication on numbers. Yes, sir. No, but you can multiply lists, you can multiply vectors, you can multiply matrices, we can multiply strings if we define what that means. Yeah. Type num multiple. Oh, so there is a constraint, but yeah, like there are more. Geez, they must have updated this since last year. Last year I was using 8.1. Okay, hold on, let me see, because addition shouldn't act this way. Okay, I have to update my slides. How about concatenation? Okay, concatenation's a better exemplar of what I'm trying to say, because you can concatenate any type of list, provided that the thing inside of the list is the same type. But we'll get back to it. Okay, so this is now out of date. I'll have to fix it. Yeah. Things that behave like numbers. If you took some math, like there's this notion of like a group in a ring. We can have things that sort of behave like numbers that aren't like technically numbers. Yeah. If multiplication on two strings was defined, it would do it. I'm not sure it's defined in this case, right? Because now there's a new constraint that says it has to behave like a number. Yeah. So, but we could like for instance, I could say take the string, like associate it with some number, like do that multiplication and then come back. Like we could go and define multiplication for these strings in part of what will be the definitions for its type class, but that's for like much later. So I'm supposed to be studying the basics now. But yeah, okay, so this is a little bit out of date. So there is a type constraint here where these have to be numbers, but it's fine. Okay, so where was I? So exponentiation is priority 8 and it's right associative. Multiplication is priority 7 and it's left associative. Addition is priority 6 and it's left associative. And you can see that bear out in this expression, right? This was evaluated first, then this was evaluated, and then the addition was evaluated. Okay, let's look more closely at this information. Oh, so it's just going through all of the things I enumerated. So infix means it's infixed, L means it's left associated, and 7 is the priority. You can ask for information about multiple functions at the same time, right? So here I'm asking for information about multiplication and division simultaneously, and it's just going to list them all out. So specifically, it's saying that the priority for multiplication is 7, and the priority for multiplication for division is 7. So begs the question, what does this statement now disambiguate to? So what does this equal? Is this 16 divided by 8 or 4 times 2? One or the other, yeah. 4 times 2, why? Yes, so that's what left associative means. It means in the instance of a tie, you evaluate from the left-hand side. So this and then that. Right associative, if this was right associative, we would have done this first, right, and then that. And that's how exponentiation acts. So we break ties on operations with the same precedence by assuming either left associativity or right associativity. So this is what it means to be right associative. So exponentiation is right associative. So this either means 4 cubed squared or 4 to the 9. So is it 4 cubed squared or 4 to the 9? given that this is right associative? Yeah, 4 to the power of 9. So we get something like that. 4 cubed squared would be this. So just to show you they're different. 4 to the power of, I don't know why that was there. Oh, sorry. Yeah, it's just to show you this expression without brackets is this expression, right? That's if you were to put the brackets there to disambiguate, that's what you get. Integer operations. So you have to be sort of careful with, you may get some weird typing problems when working with some of your homework. And it's because there are 2 types of integers that Haskell uses, and they're sort of indistinguishable in some sense. One of the integers is like an integer, which is arbitrarily big, and the other one is a machine integer, which is not arbitrarily big. It can only represent as many integers as your machine can. So just be careful. If you're getting some typing compatibility errors with integers, you're going to have to sort of designate the integers you're using as actually being like arbitrary integers. Okay, so we have floats. We're not really going to use them in this course because I don't want to deal with all of the problems that come from working with floats and having to approximate them. But just for completeness, you got 5 divided by 3. You get floats. We also have the remainder. So you remember in grade school, you could divide and get quotient remainders doing long division. So I said this to my class the other day, and they didn't know what long division was. So I'm not sure if this is sort of a lost art now. But if you were to do like 273 divided by 17 by hand, you'd have to sort of do this long division. And that long division would produce the quotient and the remainder. So the remainder of 5 divided by 3. So 3 goes into 5 once, and there's 2 left over. So you get that. 3 goes into 5 once with 2 remainders. So once is the quotient. But we also have these other operations, modulo. So 5 modulo 3 gives you 2, and div. So 5 divided by 3 gives you 1, right? So this is sort of like integer division. And this is sort of like counting on a clock, right? So if you're counting on a clock, if I said you have 11 o'clock plus 4 hours, that's 11, 12, 1, 2. Right? So that what it means to count in a modulo, sort of counting in a circle. So they look identical, but they're not. They operate differently on negative numbers. So here's laws for quotients and remainders. So recall the following property of division. So when you do x divided by y, this is equal to a quotient plus a remainder over y, if and only if quotient times y plus r is equal to x. Right? So this is the property that designates quotient and remainder. So we can express this in Haskell in the following way. If you give me x and y, the quotient of x divided by y times y plus the remainder is x, or the division of x plus the modulo of x and y is x. So here are the integer operations and how they differ. So what's divide minus 5 by 3? This always gets tricky, but here's the rule. So you just do the float division and round down. Right? So minus 5 divided by 3 is minus 1.6. Rounding down, you get minus 2. It's the same rule if you put the minus on the denominator. So you're going to round down 5 minus 3 to minus 2. If both of them are negative, right, then it becomes positive. So you're rounding down from 1.6. Okay, so how does this work? So this is where it's going to differ. So this is how you can sort of read these off. And they're not like, they'll be useful for some of your exorcism problems, but it's certainly not something that is like I'm overly concerned about everyone having a full understanding over. But if you're working mod 3, that means you have 3 numbers in your system, right, on your circle. And if you want to do minus 5, you do it like this. You start at 0 and you walk backwards. Minus 1, minus 2, minus 3, minus 4, minus 5. Right? That's how you get 1. Okay. What happens if the minus 3 is like the things that you get to write down in your circle? Well, then you get minus 2, minus 1, and 0. And if you want 5, start at 0. So 0, 1, 2, 3, 4, 5. That's how you get minus 1. What about minus 5 mod minus 3? Okay, in this case, I have the numbers minus 2, minus 1, 0, and I need to count to minus 5. 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 2. All right, so 1 is just rounding down float division, and the other one is sort of like what you'd get if you're counting in a giant circle. Just want to make you aware of that nuance. Okay, So this is the punchline from last week's lecture. So we've all sort of grappled a little bit with lambda expressions. So here's a lambda expression, lambda x to lambda y to x minus y, 3, 2. How do I reduce this? Or do you remember last week doing all of these applications? Applications was left associative. So tell me what I put into what. Yes, sir. Yes. So the way that I would evaluate this is I would put 3 into this expression, and you would bind x. Do I have that written down? Okay, so that's the Haskell expression. So I'm saying that this 3 is going to get put into here, right? So, but this is the punchline, right? This lambda calculus expression is written like this in Haskell. Right? Just that's it, right? Lambda x to lambda y to x minus y at 3, 2. Right? These are identical. That just goes into the system. So this is actually going to evaluate to 1. Because it's a lambda calculus. But how did this work? And I think that's probably on the next slide. We took 3, it went into here, which means it took x and it bound x to 3 in here. So we got 3 minus y. So what did that leave us? It left us a function in y that went to 3 minus y. And then we take 2 and we put it in that expression, and we got 3 minus 2, which is 1. Okay, so this is the lambda calculus expression, and there's a short form, right? Because remember, if we have functions that take multiple variables to things, we don't have to write it like this. We can write it as sort of lambda xy to x minus. Right? So here is the lambda calculus expression. Here is it in its short form. Both work, right? And they're already working as functions in Haskell. We can name anonymous functions so we can repeatedly use them. I know this seems kind of strange to name anonymous functions, but such is life. Okay, so here's f. I'm saying f is equal to a function that takes x to a function that takes y to x minus y. And then I can call the function in its prefix form, right? So I can say f32, and that's going to give me 1. So be careful. Like a typical mistake I see is like evaluating from the outside, right? To take 2 and put it into f, and then to take 3 and to put it into there. But there are already things that are sort of strange, right? We're used to needing brackets when invoking functions. Right? Have any of you ever used a programming language where you wouldn't have to put like the input to a function in brackets? Like, so this is a little bit strange. We can also omit the lambdas up here and get something like f of x and y is equal to x minus y, right? So this is how we define functions in Haskell. Has anyone ever heard the term syntactic sugar? Yes, 1, 2, okay. So what this means is that this goes to here as like rules of our syntax. I'm like not actually adding any language features. I'm saying like when you see this, Haskell, just write this. This is just like writing a short form, right? So you can see these two things as just being identical. It's just sort of like a shortcut in our syntax, right? But you have to still see this as a lambda calculus expression because it's this, right? It will get written to this when Haskell runs it. Okay, so we have f of 3, 2, and that's going to give us 1. So note the prefix operators can be made infix with backtick. So if you have a function that happens to take only 2 variables, then it's a candidate for being able to use it like an infix function. So if I put backticks around it like this, then it's going to evaluate to 1. And sometimes you do want to use infix operators. Yes, sir. F3 in brackets and 2 on the outside. Okay, yeah. So fx is x minus y. Okay. Now what do you want me to do? Okay, so what do you think it will do? It will be the same. Who thinks it's going to be the same? Like knowing what you know about lambda calculuses. Okay, so as a lambda calculus, what did this evaluate to? Right. So f is a function which takes a variable to a function which takes a variable to x minus y. So if I give it 3, f of 3 is going to return a function which takes something to 3 minus y. So this is going to work. And we're going to talk about that at length. I actually think I have a slide exactly about this. So remember that we are simulating functions of more than one variable. In reality, Haskell presumes all functions take precisely one input. So if we investigate what's happening here, what happens if I set g to what we get if we evaluate f at 0? I can walk through exactly what this means in our sort of if we were to evaluate it like a lambda calculus expression. So g is equal to lambda x to lambda y to x minus y. And if I want to evaluate at 0, this requires that I do a bind of x to 0. And when I take this expression and replace all instances of x with 0, you get 0 minus y, right? So this g is going to be equivalent to this lambda calculus expression. Y goes to 0 minus y. If I ask for the type of g, it's going to say anything that's a number, and then I give you back a function which goes from a to a. So the reason that it has to be a number is because we've utilized this subtraction over 0, right? So 0 minus something, right? That something needs to be compatible with 0. That's why it's saying it needs to be a number. So what do I expect if I evaluate g of 3? Yes, -3, right? Because g was a function, right? So this is the other neat part about the Haskell system, is that not only do we have the ability to partially evaluate functions, but functions are always being partially evaluated, right? Because everything is just a function which takes one input to something, right? Including a function, right? Because that was the rule of our lambda calculus. The computational model is restricted to that of function creation and evaluation. Sectioning. Infix operators can be sectioned. Note the brackets are necessary. So this is kind of a fun thing that we can do because our infix operators, sort of our lambda calculus expressions, they can be partially evaluated. So I can say we can have 1 plus 2, that gives us 3. I can say plus 1, 2, which is the prefix notation that gives us 3. I can also say plus 1 to 2. Right? So I can turn plus 1 into a section. So this is a function that is going to take anything and increment it by 1. Right? So what this is the partial evaluation of 1 into plus. And then it turns itself into a function, which I can give 2 to. So that gives you 3. So this is really useful when we start using some higher order functions like map and fold. We may want to say, here's a list, increment everything in that list by 1, and I'll be able to just say map plus 1 to it. Will this work? As a lambda calculus expression, what is this saying? It's saying, okay, I have the function 1, and to it, I am passing as input the function plus 2. Well, that's not going to work, right? Because 1 doesn't take any input. And the way that we wrote this, that's what it would imply, that plus 2 is input. If I say f is equal to plus, 1 plus, what is f of 1? 2. And so I'm just trying to get you used to some of the stranger syntax that we're working with here. Some care is required when sectioning with subtraction. That's why I hate using subtraction, because of the fact that it's also a unary operation. 1 minus 2, that's fine. Minus 1, 2, that's fine. Minus 2, 1. So like in the previous slide, this was like a section that was fine for plus. So what's going to happen here? So like one interpretation is that I'm trying to apply 1 to the number minus 2. And that would certainly error. The other interpretation is that this is the section 2 minus something. And if I give it 1, it should return 1. In fact, it's an error, which is why I don't like it, right? Even I have trouble like remembering, because like this is like a parsing sort of level thing you have to remember. What about this? Well, let's walk through it. So now that I put brackets around this, there's no way of confusing it with the negation operator, because this is the prefix call of negation. Right? So I'm taking negation, passing it to, it returns the function 2 minus something, and I give it 1, which means you get 2 minus 1, so that's 1 that works. right? I know it's strange, but you'll get used to it. You'll begin to like it by the end of the year. What about this? 1 minus, and I give it 2. That works, right? But again, just don't use negation. Use negate. It's better because it's less error prone, and it will negate more than just numbers. It will negate anything with a negative representation. But like this can be the source of a lot of pain, right? So if you do want to use the negation symbol, just like put brackets around it, even though that may not necessarily fix things either. Yes, sir. Yes. Yes.
But in Haskell numbers.
Okay, so it's because it would be silly to like let them be the piano representation of integers. Like we have hardware that's going to do the arithmetic, but from a theoretical perspective, I'm saying as long as like the arithmetic operations are done faithfully, sort of doesn't really matter. Although in our theoretical model, if there was like a failure in the hardware, that would be like, that would destroy our model. So we still have abstraction. We still want to compute with Haskell. So things that are can be made fast should be made fast. So if you look up something in Haskell, it may say, I'm a C call, which more or less means we're going to utilize the hardware for doing this arithmetic. But if you guys have interest, I can show you how the integers are created in like a lambda calculus. It's pretty interesting because you get to define addition, like from first principles, and prove things like x plus y is equal to y plus x, and prove x plus y plus z is the same thing as x plus y plus z, right? I can prove that addition is associative. So maybe I will show you how that works. Has anyone heard of Peano's postulates or Peano's integers? Yeah, the mathematicians surely have heard this, but essentially all you need for the integers, okay, so everything we're going to do in this course is like going to be done recursively or inductively. One of the powers of Haskell is that it lets us define like infinite data structures quite easily. So what are the integers if not the number 0 and a function that gets you the next thing? So the integers are 0 and a function successor. Right, so what's 1? Well, that's the successor of 0. Well, what's 2? Well, that's the successor of 1, which is the successor of the successor of 0. Right, so you can inductively develop all of your integers that way. And then I can give you a function that, given two integers represented like this, we can combine it. It's actually not that hard. You just have to move all of the successors off one of the inputs onto the other input, right? And what you're left is like one number with all the successors on, right? And so you get addition, but it's going to be slow as, right? Like adding something is going to be linear. Like that makes me want to pull my hair out, right? This is supposed to be one machine construction at most. But that is a good question, right? So remember, we're not actually programming purely on a functional machine, but we will be able to like certify our programs because they don't have side effects that are going to be our fault. Okay, so this magical $, which is an infix operator, somewhat controversial because it's redundant. It's a way of helping to reduce the number of brackets used in an expression. Now, funny enough, so if you ever become a teacher, something that you need to keep in mind is that when you have a symbol when you're lecturing, you're going to have to say it out loud. So I looked and looked about like, how does one actually pronounce this $sign symbol when speaking it aloud? And I couldn't find it in the text. I contacted a bunch of my old professors and they settled on the word apply. Right, so I'm going to call this apply, and it does make sense. So here's how the $symbol is defined. So F $A is equal to F of A. That makes it seem like it's doing nothing, right? Which in some sense is good, right? We don't want $signs being introduced to actually change the meaning of our program, but it begs the question, like, why is this useful? So if we look at the information on apply, you'll see that it has a very special precedence. What's its precedence? 0. It is the very last thing that's going to be evaluated. I think that's correct. And it's right associative, right? So that means it's always going to go to the right. So in effect, what this means is that it's going to allow us to like delay computation and also like drop unnecessary brackets. So this apply operator is something that takes a function, something from the domain of that function, and returns something from the range of that function. So notice $sign is the lowest possible precedence, which means it can be used to delay computation. Okay, so here's a $sign, pronounced apply in its usage. So instead of having 2 to the power of 2 plus 2, which is going to give us what? 4 plus 2 is 6. I can use the prefix notation to say 2 to the power of and give it 4. Well, I can also dump those brackets and do this instead. Right, so what Haskell's going to do is look at this and say, I need to give this function everything to the right of the $sign. Right, so rather than having these brackets, you can always drop a set of brackets and introduce a $sign, which makes some of your expressions look cleaner. So this is also going to work. This is the most sort of Haskell type of expression because everything's been put in the prefix notation. So it may seem crazy at this point to say, why take this expression and write it like this? But by the end of term, like most people will have moved to this because this is a lot less error prone. And once you get sort of used to what the functional paradigm is doing, you're going to want to write everything as like function calls to stuff. So this is sort of what I prefer. So no brackets there. Okay, so let's test our knowledge. Is this going to return something or error? So remember, this $sign always means, okay, so take this and hand it everything to the right, which is this, which is plus 2, and hand it everything from the right. So what is everything from the right? Or what am I highlighting? Is that going to resolve to anything? Okay, in other words, what is 3 times 2? 6. Okay, so that's going to be 6. Can I pass 6 to plus 2? Does that make sense? Oh, yes, I think so, because plus 2 is a function that takes one variable and increments that variable by 2. So this should be 8. And what's 2 to the power of 8? Where are my computer scientists at? You should know this. Shame. Shame on all of you. Yeah. 256, which happens to be a word. Okay, what about this? Is this going to work or is this going to fail? Some thumbs down, thumbs down, thumbs down. Okay, why? Why thumbs down? Yes, sir. Yes, exactly. Okay, so let's look at this. This will become 4. So just see it as 4. And this means pass the input, the section times 30 to the constant 4. But 4 is just the number. It's a literal. It can't take sort of input, right? So this is going to fail because giving times 30 the section to 4 means apply the argument times 30 to the expression 4, and this has no meaning. It'd be great if Haskell gave errors like this. It'd be fantastic, but it won't. So let's try to see what the error is going to be in this case. Yeah, so it's saying I can't. You're usually going to get errors saying that I'm not able to find the appropriate super type for this operation to actually work. Because there's like a type inference system at play. It's always going to try to evaluate it by moving to a space where it makes sense, right? So if I wanted to add the integer 2 to the number 1.3, Haskell's able to do that because it knows it can promote 2 from an integer to a float and then do that arithmetic. It's trying to find some compatible super type for the number 4 being able to be passed this section, but that's why I hide the errors. Don't feel too bad. Maybe ChatGPT, throw it in. I don't know, maybe, right? That'd be a use where I'd be totally fine with you using ChatGPT to say, can you please help me like unravel the mystery of what this Haskell error code means? What about this one? Does this one become okay? It's hard to see the difference between this expression 9 and the expression at 1. But 2 to the power of 120? You think that's going to work? We have 64-bit machines, right? So it's like well beyond like what a machine integer should be. All right, so this is like a mathematical, so this is a system that we want to use in math. Like, what would you hope the answer is going to be here? Do we hope that it's like hardware overflow error, or are we more optimistic than that? Yeah. Oh yeah, we could, yeah. So that's sort of my field of symbolic computation, I would say. Why even expand it? They're both equivalent and one is a lot more compact. In Haskell, it's just like, sure, here's your number. You can have your integers can be as large as you want them to be, provided that they fit in your memory. And this is important, right? If we want to use Haskell for like doing math, right? Having arbitrarily large integers is the thing that enables us to like not use floats, right? Because any number we can represent as a fraction, but we need fractions of like arbitrarily large numerators and arbitrarily large denominator. Okay, so the expression at 9 is equivalent to the expression at 12. And like which one do you prefer? Which one's more readable? Right, so I would say 9 is more readable than 12. So it's up to you, right? Whatever you find more readable and less error. Like we're not going to evaluate the style of your Haskell code, but you do have to be very careful with how you're writing down things, because it's really uncomfortable to switch these paradigms. Let and where. Okay, so we have a notion of scoping in Haskell if we have to, or we'd have like a real tough time at naming things. So we can use the where if we want to define something afterwards, and we can use the let if we want to define something before. But like it doesn't matter, because as we'll discuss soon, it doesn't matter the order at which we type things into files. There's like limited scenarios where order matters in Haskell. So I can say x is equal to y times z, where x is 2 and z is 3. And I can say t is equal to let y equals 2, z equals 3 in the expression y times z. If you want to write such an expression in the REPL, you have to put semicolons to indicate new lines. Let x equal 2, y equal 3, z equals 5, and x, y, z. So these y's and these y's like aren't the same y. I should have made them something different just to emphasize this, because the day one I said equal means equal. Well, to make that more refined statement, sort of like equal means equal within the relevant scope. Right? Because I taught you how we can like, when we're evaluating Haskell expressions with name collisions, there's like a mathematical way of resolving it. I don't expect you to know how to do it. I just said, here are the rules. Right? Suffice to say, Haskell knows how to resolve name conflicts. It essentially turns every variable into like a variable with a number. It makes them all different. Lines that start with the same indent level are presumed to be grouped, right? So now we need some mechanism of like notating or denoting what the scope is. So Haskell is a language where like spacing matters. It doesn't matter how many spaces you use, but everything at the same indent level is going to be presumed to be in the same group. So most of you have done Python, so you should be used to the fact that like spaces are meaningful. Okay, so here is something that's super important. There are things that you can do in the REPL that you can't do in a file. And the reason is the REPL is special. Like the REPL is an IO environment, right? It's presumed by context that you're doing input output. And when we're doing input output, things become quite special in Haskell. So like there is a joke on the EdStem that like, I have to show you all, like we basically have to do 12 weeks of this course before I can explain to you how print hello world is referentially transparent. And that's true, right? One of the last lectures I'll do is showing you, look, we can print. That's something that's like within our capacity. But that's all the REPL is doing. So we're going to shove all of the sort of theoretical sort of considerations that are required to understand how that works. And at this point, we just need to understand that there are things that you can do in the REPL that you can't do in files. Okay, so look at this file. If I call it in to Haskell, you think it will work? Because like if we study this, I'm saying x is equal to hello. Hold on, I just have to share again. Because I have x here, and I'm saying x is equal to 2 times y times z. But do y and z exist yet? Well, that's true in a state-based system, right? Because in imperative programming, like sequencing is something that's important. right? The lines are evaluated top to bottom. We're not in the imperative programming paradigm. We have no notion of sequencing. Our philosophy is that equal means equal. If I were to write these in math, does it make sense? Does order matter? Not really, right? In math, this is fine. Oh, x is 2 times y times z, and y is 3 times z, and z is f of 1, and f of x is x squared. So this is going to work, right? X is going to be 6, z is going to be 1, right? So it handled like the scoping, and like it did not matter. Any permutations of these lines are going to produce the same programming. No sequencing. Now the problem is you cannot do the same thing in the REPL, because the REPL again is special. It is doing a sequence of commands. So I can't say x equals to 2 and then x equals to 3. I can't say z is like t times s, because those don't exist yet, right? So be careful, right? The behavior in the REPL is not identical to behavior that you can get in files. The indentation level of an expression defines its scope. So if I say x is equal to y times z, where y is equal to z plus 1, and then set z equal to 2, is this going to work? But if I gave it away already, it went in fine. Right, so everything at like 0 indents has the same scope. So thereby this z is 2, right? It can see it. So this is going to give us z is equal to 2 and x is equal to 6, right? Because this is sort of like in the global scope. Y is not in the global scope because y is buried in this expression at an indent level. So in the REPL, I can't ask for its value because it's like a locally scoped variable. Okay, so 2 options. We can either keep going, I can let you out early, or we can have a 10-minute break. Which would you prefer? Okay, so silence means I'll continue, but don't say I didn't offer. Strings. I'll just check that the chat's still with us. Chat, any technical problems that you need corrected before we move on? Nope. Okay, let's go. Okay, so strings are something that like is definitely out of place. We haven't talked about the simplest of data types, let alone a data type, which is basically a list. But most of these exercism problems that you're going to be coping with will deal with I/O, right? So I have to teach you a little bit of I/O. I have to teach you a little bit about string processing. And furthermore, as like a practical consideration, you're going to want to like look at the output of your functions, right? So I do have to talk about I/O in order for us to be able to work at all. Although we won't be able to lay a theoretical groundwork for it until the end of term. So types are very important in Haskell, right? Because Haskell has what's called the type inference engine. So we're going to be, you don't have to declare a type when defining a function, right? That Haskell is going to infer its most generic type called its principal type. We'll talk about soon, and it's some of the content of your assignment. But we already saw how to use the type operation. So type on multiplication, and this time I did put number in, but provided you give me a number or something that behaves like a number, I am a function which takes a number and returns to you a number. Or sort of more accurately, I'm a function which takes a number, which returns a function which takes a number, which gives you a number. That's what multiplication is. So even though I/O requires some extra treatment because I/O is a side effect, as I said, if I write a bunch of statements in a file, the order is invariant to like the behavior of that file. So what does it mean to put a bunch of print statements in a file? Like, isn't the order super important to like define the order of the outputs of those prints? Like, so already printing is like a problem in our system. So I'm gonna have to show it to you anyways, though. Right, so we can actually see output from stuff. So I/O is a side effect. We introduce the string and char data type. I/O is pretty important, and a lot of exercism problems are on string. So it's just to give you enough Haskell so you can play around. So we do have characters in this system. That was not true of Python. It is true of Java. You can read these double colons as has the type. So here we can say X has the type char. I can say X is Drake. We usually pluralize something if we were to like to indicate that it's a list of something. Drake is terrible. I have like an ongoing sort of battle with him. I think he's the worst Canadian artist to ever come out of Canada. I know you're listening, Drake. So if you ever see Drake slams drizzled across my slides, that's why. Okay, so what's the type of X's here? So this is going to say, I am a list of characters. Right, so this is how Haskell denotes a list with these square braces. If X's is D now with double quotes, the types of X's is like also a list, right? So there is a distinction between D, the character, and D, the singleton list of a single character. There's also something we call a typed synonym. So these are a lot like these syntactical sugar that we're using. String and list of char can be taken as equivalent and as synonyms to one another. So we could have said the type of X's is a string, or when you're like writing your type signatures, you can use string instead of list of char, but we'll get back to that later. Types are always capitalized, right? So again, Haskell is a case-sensitive programming language. So you're not allowed to name anything with a capital unless you intend for it to be a type. And you can do reassignments in the REPL, but not in a file. So be mindful that there are differences like this. Printing from the REPL is easy, right? So you can just say print hello world. What's odd about this print statement? No brackets, right? Because what is print? What does it has to be in Haskell? What is everything in Haskell? A function. So print is a function which takes a string and like puts that through IO, right? And note that quotes here are included. I can put a string line, right, which is different than printing in that it like drops these sort of quotes and is properly something like putting something out along the IO buffer. I can put string without a line, and then you just like lose the tailing case, right? So these are sort of relevant for when you're doing your exorcism problems. So printing from a file. So we have files. I said it doesn't, like with some limited exceptions, it doesn't matter the order which you type your lines into that file. And thus printing doesn't really make sense in that context. So what Haskell modules typically have is, and in fact, they're presumed to have this, is a function called main, and main's type is IO. And so at the end of the year, we'll deal with this, but we'll find out that we can actually have a type called IO, which is a special state transformation, which allows us to do IO operations in a functionally pure way. So each module is presumed to have such a function, and all this function can do is output stuff, right? So I can have a main function which puts string line hello world. Because if we look at the type of put string line, you'll see that it's outputting IO. So the only functions that can be called right within that main have to have the same return type. Right, so I can load this foo, one module loaded, and then I can type main, which is a function which takes 0 inputs. So it just sort of executes. We sometimes call this a procedure, and you got hello world. So just notice main has type IO, bracket, which is a special type, which we use when running a program involving input and output side effects. The only way that you can print from a function is that if that function returns IO. So this is going to be kind of frustrating. Why? How do we debug in the imperative programming paradigm? Well, you just go into your function and print out the state of all of the functions during runtime. You're not going to be able to do that here, right? Because the only way you can see something from your function is to give it a return type of IO, which means you've changed that function. And so a lot more planning has to go into this. Like the hack and slash, there's not really that good Haskell debuggers. But the good news is once you get something that's like syntactically correct, it's normally working. So printing to the screen is a side effect, and therefore printing the output of a module must be wrapped by this type. So GHCI understands context when entering functions into the REPL, that IO operations are being conducted. Do. Okay, so I've shown you how to like print one thing from main, but like what happens if you want to print like a bunch of stuff from main, which is also going to be the function which like runs your main loop, so to speak. Right? You're going to like our strategy is going to be to take a problem, decompose it into a set of functions, and then tie these functions together to perform a single action. And that single action is usually going to be packed away in your main function. So you want to like be able to execute a bunch of stuff. Right? So there's this syntax called do, which requires a monad, which is like something that we're going to discuss at the end of the year. But the do syntax is used when sequencing actions like the sequence function calls that comprise your main function, right? If I want to say like get user input, then give it to this function, then print. You need to do it in a do. So do is not what you may think it is. It's not a loop, right? Do, it's, if you want to think about it as a loop, it's like a loop that provides exactly one iteration, right? So do in Haskell is a is a control structure which permits you to like execute a bunch of imperative style commands, like do this, then do this, then do this, then do this, then do this. The structure is necessary as Haskell modules are unordered. So here's a function which can print two things. So now I say I have a main function. It's of type IO. It's defined to be doing print this line and then print the next line. So that's how you print two things. Let's talk about concatenation, because these are just going to be sort of functions that are going to be like super useful to you when you're doing your exercism problems. Okay, so if I want to take the string killer and the string magpies to get killer magpies, I've dreamed sometimes that I'm murdered by killer magpies, right? Because I bike to school and they attack me. There's like cars going by, so I think my days are numbered. And I had to put like stickers on the back of my helmet that like are eyes, and like they just don't work. In Canada, we have like aggressive animals, but they attack you from like the ground. Like even the winged animals will attack you from the ground and from the front, which I feel is a lot more honorable than attacking you from the sky, from the back. Right? At least you can, you got a chance to defend yourself. But in any case, this is going to give us the concatenation of these two strings, which is going to be useful. We can, like, it's my preference to have everyone shift to this prefix notation, right? Where instead of saying killer plus magpies, we have the concatenation function, which we pass killer, and then we pass magpies to that to get killer magpies. But if you ask for the type of concatenation, I think we already saw that, but what would you expect here? Like what is the largest category of things that we can like concatenate? Lists. Okay, but we've got to be a little, it's not all list, right? I can't take a list of integers and like concatenate a string, which is a list of characters. So we need one more thing about our list. Yeah, so you need at least two lists, and the thing inside the list have to be of the same type. So we express that in Haskell like this, right? Saying the concatenation operator, like it's not something that just works for integers list or just works for character list. It says, look, anything that's a list, I can concatenate with another list, provided the thing inside the list is the same. And that's what this is saying. Right? I'm a function which takes a list of type A and a list of type A and returns a list of type A. Right? So here, like if this is meaningful, that this is the same A as this, like they really means same. This is where the type inference engine is coming in. And that's what we're going to strive to do in this course, right? I don't want to write one concatenation operation that works for like a single type of list. I want to write functions that are going to work for like the largest category of things that it makes sense for that function to apply to. Yes, sir. Well, a char isn't of type list, right? So it's, but then it becomes a singleton list of char. It becomes a list, right? It's just a list of a single character, right? So we're never going to be able to concatenate characters. The same way we'll never be able to concatenate integers, although we could define what concatenation means. And if we wanted to define concatenation over integers or chars, we could. I'll show you how we do that later. It would just mean that sort of concatenation has to satisfy a bunch of properties. And as long as the new concatenation operator that I defined has the same properties, we'd be fine. So we'll get to that later when talking about type classes. So here you go, like we expect this to work, right? Because these are two lists and they both have integers inside of it. So yeah, and you can sort of understand like how would the function for concatenating list of characters like meaningfully differ from functions that like concatenated list of integers? Like it wouldn't, right? It's sort of like this is a function where like the thing inside, it's like it doesn't matter. We're going to be doing the same thing. Polymorphism. So the reason we can have polymorphic types, like, you know, a list of anything, is because Haskell can infer types. So the fact that it has a type inference engine is like one of the defining features of functional languages. So Haskell is going to enforce type compatibility. Many of the errors you're going to be dealing with at first are going to be because like you have incompatible types going to functions and you have to sort of sort it out. This is a little bit different than like the lambda calculus we were using because we didn't talk about types in our lambda calculus, right? The generic one we talked about was called an untyped lambda calculus. So you just need to know that Haskell is a typed lambda calculus, but all that effectively means is that we're going to generate type errors. An untyped lambda calculus essentially assumes everything is just in like some huge super type, but just know, right? So what Haskell is going to try to do here is say, okay, I have a list of 1, 2, and the list of like the strings 1 and 2. Is there some larger data type for which both 1, the number, and 1, the string exist in, right? Where these can play. In the same way that like, if I were to try to do this with 1 and 0.5, Haskell would say, is there a super type where like both the number 1 and 0.5 can live? And in that case goes, yeah, it's floats. So it's from whatever you think that floats. Here it says, I can't find, there is no type where the number 1 and the string 1 are like compatible with one another. And that's why I'm going to refuse to do this, right? But you're not going to get, like this is a typing error, but it's not saying incompatible types here, right? Which is what it would say in Python. So you do have to get a little bit, you know, some of these errors require some digging, but essentially that's what it's saying. There's no instance, there's no type where I can take a number in a list of characters and like operate on them. Type classes. So more on this later. So I may use this term without strictly defining it, but you can just sort of hear me say like a collection of classes. So like there's the number class, which is like the collection of all types that behave like numbers. So like integers are in that, machine integers are in that, floats are in that, fractions, like these are all things that behave like numbers, right? The important thing is that they're going to have addition, subtraction, multiplication, and division defined on them. We're going to be making our own type classes. We can add other types to type classes, but we'll talk more about this later. Scoping. So we discussed that indentation sort of defines belonging in a control structure, and those control structures have their own scope. So I have two functions here that return IO. One is the main function, and one's a different function. So what will happen here? So here, will this function be readable by main, this vision function? Yeah, because main and vision are at the same indent level. So what this is going to do, it's going to put string line wise, where wise is equal to black. So that's in its scope. And then it's just going to call this function vision, which then just puts this string line lotus. So this is going to print black lotus. The black lotus is the most rare Magic the Gathering card. It's, I think it's worth like, I don't know, I think last time I checked like $500,000 or something like that. So if you get a black lotus, you give it to me, you get a 7, right? That's the type of exchange I'm willing to do. Operations on strings. So what I want you to avoid at all costs, for reasons that we're going to talk about, is using indexing. That's not, indexing is not a functional sort of like part of our paradigm. Not really. What we want to do is solve everything inductively or recursively, which means when you're processing a list, you're not really going to say process like the ith and jth element. You want to say something like, give me the first member of the list and then recurse on the rest. Right? So we're always going to be taking the head off the list and recursing on the tail, or taking like the first three members of the list and recursing on what's left. So here are the functions that allow you to do that. So I can say type take. So take is a function which, given an integer and the list, returns a list. Right? So you don't even, often when you just need to be given this type contract, this type signature, like to figure out how to work the function. Like there's no usage example here, but how do you think this function works on a list? Like what is the syntax, the type? It takes a number and then a list returns a list. So I just do something like this, right? I give it a number and I give it a list and it returns a list. So taking 3 from here is going to give 0, 1, and 2. Dropping 3 from here is going to remove 0, 1, and 2 and give back the rest. And so this is like how you get the beginning of the list and like the rest of the list. What do you suppose the type of a function length is? Takes in a list and returns an integer. More broadly speaking, length should be a function that takes anything that has a notion of length. Right? So list, yes, is part of that. Lists have length, but trees can have length. Graphs can have length. So this is why it's going to say anything foldable. I'll take anything foldable, and then I'll give you back an integer. So at your stage, and I think maybe we won't really talk about foldables. You can just read this as list. But what a foldable is something with an inductive structure, which you can like walk through and count your steps, right? Because more than lists have length. And so, but I'll still give the points, right? Something that's a list and an integer. So what's the length of 0, 1, 2, 3, 4, 5, 6, 7. Okay, so here's indexing, and it comes with like a sex ed joke. Okay, so I'm going to, like sex ed, I'm going to show you how to do something unsafe and then hope that you don't do it, right? So here is how you like index in Haskell just for completion's sake, but don't do it because it's unsafe. Okay, so the type of the index operation is this, right? Give me a list, give me an integer, and I'll return something in that list. Why is this a problem? Why do you suppose I'm saying don't do this? What makes it unsafe? Index out of bounds. You don't know ahead of time if you're going to walk out of bounds or not. That seems to be in total conflict with what we want to be doing in Haskell, where we guarantee no side effects. Like stepping outside of bounds is certainly a side effect. So if you do use this indexing, you better make damn sure that like the function, that the list that you're indexing, like will actually provide you that index, or you're going to get an error and the whole thing's going to crap out, which is why I say don't use this. Don't use it. I'm just giving it to you so you can read other people's code online. So this question is basically like, what is Haskell a zero index language or not? Do we start count? Is the first index 1 or is the first index 0? Error. Do you think error? Oh, 0, 0. Yeah, it's we start counting from 0, right? So we could. This is also an infix operator, but I'm saying like to the indexing function, give this list and this index and get back 3. And I'm trying to slowly move everyone like to using these type of statements. Okay, but if I asked for like what's indexed at like the length of this, like it's too large, it's not going to work. Which sort of like like this isn't really a function, right? Because it doesn't have definition for its entire domain. It's not what we call like a total function. So we want to strive to make all of our functions in Haskell total. It just requires I give you one additional type. So there's a type called maybe. So we could make this indexing site safe by saying, give me like a list and an index, and I'll maybe give you back an element from that list. And otherwise I'll return nothing, right? So that's our way. That's basically going to be Haskell's version of error handling, right? The fact that I can introduce this maybe data type. Here's a function called head. Here's its type signature. What do we suppose it does? Yes, sir. Start of the list. Could you be more specific? And just the first element. Yeah. So head of 0, 1, 2, 3, 4, 5, 6, 0. What do you think the tail does? So what's the type signature for tail? Yes, sir. Given a list, I'll give you back a list. So tail of this gives you that. Now this is much more preferable because I believe like tail will work on an empty list. Oh, no, it won't. Will head work on an empty list? No, it won't. So never mind. They're also sort of unsafe. But this will become safe if we pattern match, which is something I'm going to show you when we start talking with lists. So this will also have to be treated carefully. It doesn't make sense to me why we can't have a tail of an empty list. Let's see, tail of this. That should be empty list. Okay. The index operation, or like working with lists and trying to index with them, is like an unsafe operation. So we have to be careful, right? To really make this fine, I have to give you this maybe data type. So we generally try and avoid using unsafe functions because we don't know they're unsafe until runtime. Yes, sir. I don't know. The head of an empty list. Yeah, the head of an empty list makes sense for it to fail, but it doesn't make sense to me that the tail of an empty list couldn't be tail, because it's the thing that you want to add to it to like get the thing back. But if there's no head, then I guess you have no tail. But this is something we're going to solve in pattern matching. Anyways, the point is that we have to be careful in working with lists, right? Because they have all of these unsafe functions. Okay, so here are some handy tricks when working with strings in your exercism. So if you want the alphabet, you can use these like 2 dots. You can stride through data types. So I can say, give me A to Z, and then concatenate the capital A to Z. So that gives you the alphabet. And then I can say things like, is 2 an element of the alphabet? Right, so what do we suppose the type for element is going to be? Well, something that acts like a list, something that admits equality. This is going to be something we're going to have to pay close attention to. So you give me sort of an element of the list and a list, and I'll tell you if that element of the list is in the list or not. So something like LM2, that corresponds to that. And then 1, 2, 3, that corresponds to that. And you're going to get a bool back. So that's false. You can ask if something's not an element. So is 2 not an element of the alphabet? That's true. You can get the numerals 0 through 9. And there's a cool thing I want to show you about Haskell. So Haskell, the whole thing is delayed computation, whereas in the imperative paradigm, we do something called eager evaluation. Everything is evaluated as soon as it can be evaluated. But I said we're going to be defining data structures inductively, and some of these data structures are going to be infinite. So what that means is that like it's permissible to have infinitely large data structures in Haskell. So what is this? So I'm going to ask Haskell to give me a list of all the numbers starting from 1 onward, all of them. Will this work? So how does this work exactly? Like, what are the operations on lists that I've shown you so far? Like indexing, take, and head, right? So can I get the head of this? Python's like, yeah, here you go. Here's the head. Can I like, get the 100th index from here? It's like, yeah, sure. Here's the 100th one. No problem. What happens if I ask for the tail of this? Any guesses? It's like, okay, here you go. You asked for it. But this is only a problem because like I'm printing it, right? It's if I wanted to do something like, yeah, like give me the tail of X's and like what's the head of Y's. That's fine. I can even do like, we're not here yet, but I can say, yeah, like map +1 to everything in Y. So now what's the head of Y's? It's 2. Head of Z's, 3. Right. So I can even like operate over those like infinite data structures. Right. Because Haskell's, I'm saying Haskell, can I have the third member of this list? It's infinite. It's like, sure. Can I have the 100th one? No problem. Can I have the 10 millionth one? Sure. Because at no point can you ever ask for like to do like I can't. Can you give me an example of a function which like I can't do on an infinite list? Yeah. Can't get the last element. I can't add it, right? But I can do things like zip them, fold them. Oh no, not fold. Zip them, map them. So this is really interesting, right? The fact that like we can have data structures which are infinite, and that's fine. Yeah. No. Because like you won't know where to, well, let's try. So if I have X is equal to this, Y is equal to this, like this would be fine for typing, but I'm not sure what it would return. I'd have to guess this can't work. Maybe it would. Nah, doesn't work. Oh, sorry, yeah. I need to do infix. Oh, it did work. Neat. But you're never going to get to Y's, right? So like this as a delayed instruction, this may be like, okay, I'm going to concatenate this, which means if I hit the end of X's, I should go to the beginning of Y's. But you're never going to hit the end of X's. But yeah, we're not going to be able to do things like take the length of this or like actually traverse any of Y's. But this is like one of the fun parts of working in Haskell is having such infinite structures. Yes. Oh, yes, but that's semi-computable. So I expect this is going to run forever. Yeah. Do you know what I mean by semi-computable? So let's remind ourselves about this. Okay, so I'm saying X's are like all the numbers, the natural numbers, essentially, all of them. And I can say is like 7 an element of the natural numbers? Yeah. But is -1 an element of the natural numbers? It's not. But it's not returning false. What's it doing? It's checking all of them. And it will. It'll keep checking all of them until it's stop checking. Right. So this is something called being semi-computable. If there's an answer, it will return it. Right. So if it's true, it will stop and return true. But otherwise, it will run forever. So isn't that interesting? Yeah, I'm going to give you some homework with infinite data structures, which will be quite interesting. Okay, so just to get you started on your practicals this week, I'm going to talk about how to define functions. So the exercises and problems I gave you this week are dead simple or arithmetic stuff, but you may be frustrated because you're going to be getting a lot of errors maybe. So the practicals will have 2 TAs this week just to help, but don't get discouraged, right? There's a little bit of a learning curve at the beginning, right? Because you're going to be trying to do everything imperatively. Like you have to like just let go. Like don't try to bring your other programming knowledge to bear in this course. It's going to be harmful because we don't have loops. We don't have if statements. It's a different ballgame. Or you're going to have to start trying to force yourself to think recursively. So don't reach for do. That's not a while loop. Don't use the if expression. Right, there's something in Haskell called an if expression, which is different than an if statement. So don't try to look up more Haskell stuff. Because usually when you look it up, you're going to be fed like the most sort of sophisticated version of the thing that you're trying to do. People will be using like the highest level language features for, I want you to engage with these programs, like using the tool set that I've given you. And you can see my solutions. And like the solutions that I wrote are like in line with like what I've taught up to this point. So just keep that in mind. Like the solutions for your practicals are available, but you shouldn't look at them until you've done the question yourself. I actually think you may be locked out of seeing my answers until you solve it yourself, which I'll try to figure out a way of giving them to you. Okay, so here's the simplest way, in some sense, to define a function, period. You just tell it, like, you define the output for every single possible finite input. Like this is somehow how like grade school children think calculators work. That someone just said 3 + 2 is 5, right? And 77 + 3 is 80. There's just a giant table that it looks up into. So we don't have XOR in the system. Here's how you would be able to define XOR in the system. Like I can just say XOR is a function which takes a bool and returns a bool. Here's how I define it. XOR true false is true. XOR false true is true. XOR false false is false. And XOR true true is false, right? This is a function definition where I've declaratively set the function. Right? So we do have we're working with some of the declarative paradigm here by not telling the computer how to compute something, but declaring what that computation should be. Right? So this is going to work. So I can say false XOR true, true. What's the type of XOR false? So XOR is a function which goes from bool to bool to bool. If I give it one bool, what do I get back? Well, so how does this always work? So XOR gets a bool and it returns bool to bool, right? So the type of XOR in given false is a function that goes from bool to bool. So this is obviously not the best way of defining functions. Why? It will only work if the domain is finite. Like the domain may be big, right? I don't want to have to write a program to like write programs in Haskell. It sort of defeats the purpose. So we can have something called conditional guards. So these conditional guards are one of the places for which order matters. And it's also the case here. The first pattern that Haskell can match top to bottom is going to be the one executed. Right? So just keep that in mind, right? This is one of the places where order matters when you're defining a function. So suppose I want to have a function that given two integers returns the bigger one of those integers. You could do it by using guarding. So here I can say bigger x and y. So this is going to be a function that takes an integer and returns an integer. And I can say if x is greater than y, or in the case that x is greater than y, I am equal to x. And in the case otherwise, I'm equal to y. Otherwise is a type synonym for what? Can anyone guess? Otherwise, I basically want to say if all other branches do not match, do this one. True, right? So you could actually put true there and it would have no effect. So this is why the order matters. I can't put otherwise first, right? Because then it would match everything to that otherwise. Now, we could remove it so that the order could be permuted, but then we'd have to like, for every line would have to say what the condition to be in it is and the condition to not be in it. That would get quite messy and often semi-computable. Well, I can define a function like this using guards. I can say bigger 1, 2. So this bigger takes the number 1, which then returns a function, which then takes 2, which then evaluates to, I would say, 1, right? Because I'm not answering, 2, sorry, the bigger one, 2. Basic recursion. So I'm going to talk about recursion at length soon, but everything in Haskell has to be defined recursively. And you should have engaged, like all of you should know what recursion is, right? From like a very basic level. Okay, so the basics of recursion is that the function can call itself, and the function should traverse, like should be calling itself on smaller input so that it eventually triggers some base case, right? So here's how you can define the factorial function in Haskell. So I'm just going to declare that the factorial of 0 is 1. And then I'm going to say factorial of x is multiplying x by the factorial of x minus 1. So I can say things like fact of 3 and get 6. My question is, what happens if I call fact of 3.1? Yes, sir. Pardon me? Infinite loop. Why? Well, because it went from 3.1 to 2.1 to 1.1 to 0.1 to minus 0.9. Anyways, it jumped over 0 is the point I'm trying to make, because we didn't give this typing information. If I would have said fact is a function which takes an integer to an integer, then we would have been prohibited from passing 3.1 to it. But because Haskell has a type inference engine, it will deduce the most generic type for this function, which is in this case going to be, I can go from A to A, provided A is anything that behaves well with multiplication and subtraction. So probably like some type of number. Okay, so the last thing I want to do today is write this function just to show you how we can do it. Is that true? Yeah. So has anyone heard of the Culott's conjecture? All the mathematicians, surely. This is fun because it seems super simple, but it's like yet something that we have to prove. So it seems to be the case, this is why it's the Culott's conjecture and not the Culott's theorem, that if you take a number n and you undergo this process, that you'll always end up at the number 1. So give me a number. If it's even, divided by 2. And if it's odd, multiply by 3 and add 1. And if you iterate on this, you'll eventually hit 1. And it seems to be true for like any number that we check. We still don't have a systematic proof demonstrating that this is the case. So you guys can give it a go. I think this may be a millennium problem. If you did this, your career as a mathematician would be set. But it's interesting that something so seemingly simple is like not within the reach of like the most sort of up-to-date mathematics. So what I want to do is just write a function which, given a number, returns the number of steps required to iterate to 1. So let's give that a try. Okay, so the first thing I want to do here is let's call it Culott's. What should its type be? What do I want to take in and what do I want to return? So I want to take in an integer, and then what do I want to give back? An integer. Okay, so I want to take an int and return an int. Okay, so this is going to be a recursive function. So the first thing we better think about is what's the base case? What are we descending to ultimately? 1, right? Because I think it says here that it has to be strictly greater than 0. So I can just say Culott's at 1. How many steps does it take to get from 1 to 1? 0. Okay, so now we have to use guards. So here's Culott's. I always make a mistake by putting equal here, but you don't, right? Because the equal comes with the guarding here. So what are we supposed to do? If n is even, then divide n by 2. So I can do it like this. There's a great function called even. So if n is even, so Culott's at n. If n is even, what do I want to do? I want to say, so remember we're counting. So I need to say 1 plus Culott's at, I have to divide n by 2. So divide n by 2. Okay. And then otherwise, what do I want to do? It is 1 plus Culott's. It's 3n plus 1. So let's see if this will let me load it. Okay. So Culott's at 7, 16. I think that's correct. Okay, but let's change this, right? Because this is not I don't like this style of doing the arithmetic. So let's change everything to a prefix. So that should be 1 here. If I put a $sign there, that means I can get rid of this. If I put a $sign here, that means I should be able to get rid of this. So okay, so I always recommend that you do many reloads, right? You try and load it every time you make a change. So let's do the same one here. So I put plus there, a $sign there, which allows me to get rid of this. I can put a $sign here, which should allow me to get rid of this. If I put a multiplication here for 3 and the n, then I have to be careful because I need to add a 1 to that. So the 1 should be like this. Hopefully that will work. Yes. Okay, so I know this seems ridiculous relative to the first thing, but believe me, once you start working with Haskell, this type of statement is going to make more sense because you're going to get used to passing things in. Okay, so there's our first little Haskell program. This should be enough Haskell for you to engage with some of your exercism problems. So next week we're going to pull we're going to go back again. Right, so I'm going to talk much more specifically about types and types classes. So from now on, we'll be building Haskell. So good luck. I'll try to come around to some of your practicals, but it should be fun to get your hands dirty with the system. See you guys next week.